In the second part of this chapter, we will start with the equilibrium. You remember equilibrium from General Chemistry 2, when the rate of forward reaction becomes equal or very close to the backward reaction, we will have equilibrium, means reaction works both ways. What we needed to determine for the reactions was, for the equilibrium, was equilibrium constant, which is the product of the products to the power of their to the power of their coefficients divided by the reactants to the power of their coefficients. So for such a general reaction, A plus B gives C plus D, this is a K equilibrium. What we needed to keep in mind that we never put the concentration, and these are the molar concentrations. We never include the molar concentrations of solids and liquids in the equilibrium, K equilibrium equation. Like here, when you have, this is an example of organic chemistry. The same rules apply to different compounds which are organic compounds now. HCOOH plus H3OH gives that compound HCOOCH3 and H2O. This is, you will see in organic chemistry too, which is called esterification. So since all the coefficients are 1, there is no exponent, but water is liquid, its concentration does not change that much, so it's not entered in the equation. So it's HCOOCH3 divided by the reactants. That's how you write the K equilibrium for reactants and products for organic reactions. And if you want to work one more on these examples, you can work on SO2. SO2. This is a gas. It should have been mentioned this is a gas, which is not. I will include it for you. And it gives SO3. Before you write the K equilibrium, you need to make sure that reaction is balanced. It's not balanced, you have to balance this equation first. You will see 4 oxygens and 3, so you put a 2 here, make it 6. Now you have 4 and 2. So K equilibrium, since they're all gases, is going to be SO3. What is the coefficient for SO3? 2. And divided by SO2 squared times O2. You can work on the rest. You have on page 11. Make sure they're all balanced and then write the K equilibrium. But the next thing we need to know about K equilibrium is how to interpret it for a reaction, because an equilibrium doesn't mean that the rate or the equilibrium is the exactly same towards the products as towards the reactants. Sometimes you see the equilibriums like this. Means that a small part goes back or a small part goes to the front. So let's see, like if a K equilibrium is much more than 1, like here, when K equilibrium for the reaction is 1.8 times 10 to the 5th. It's a huge number, means it's going towards the products big time. Just a little bit goes back. It's towards the products. But when K equilibrium is much smaller than 1, then like let's say you have a K equilibrium which is 1 times 10 to negative 12. It has 12 zeros before 1. It's a very small K equilibrium, means that when you have A plus B, just a little part goes towards C and most of it goes back towards A and B. And it is obvious here because if K equilibrium is products over the reactants. When the top of the reaction is higher, then the K equilibrium is higher. When top of the reaction is small, the bottom is higher, then K equilibrium is low. It's just a mathematical relationship. For example, this is what happens when there's lightning in the sky. Delta H for such a reaction is 68 kilocalories. K equilibrium is 2.68 times 10 to negative 29. So oxygen changes to ozone. Let's answer these questions based on the given numbers. First, is the reaction exothermic or endothermic? Delta H is positive. Endo and exo, they are related to delta H. Delta H is positive, so this is endothermic. It absorbs heat. The second one, is the reaction favored by entropy? Why do you think so? Let's calculate delta S. 3 moles to 2 moles is 2 minus 3, which is negative 1. So, it's not favored as far as entropy, if the entropy is decreasing. C, why does this reaction require lightning to occur? Because it's not favored based on entropy and it's endothermic, so it needs some energy to happen. And for D, are the reactants or the products favored at equilibrium? At equilibrium, we will have to pay attention to K equilibrium. It's a very small number. K equilibrium is very, very smaller than 1. So the reactants are favored at equilibrium. So that's why we need the lightning to make it happen, to change oxygen to ozone. Going back to our cyclohexane, you remember we had axial and equatorial. And you remember the ring flip? By ring flip, axial positions change to equatorial, equatorial change to axial. K equilibrium is 2.7. And you remember what happened? You had diaxial interactions, right? That's why K equilibrium is more than 1, and this reaction is favored towards when there is no diaxial interaction. That's what we said before. Now we are proving it with the numbers, with the number for K equilibrium. This is a stable because there is no diaxial interaction, and it's going to happen spontaneously, but delta G is less than 0. And one more thing you had is delta G, the relationship between delta G, standard, and K equilibrium. When K equilibrium is negative, delta G is going to be, K equilibrium is smaller than 1. Then LNK is negative. Then delta G is positive. You can easily try it with just plug in one K equilibrium value and try it. When K equilibrium is more than 1, LNK is more than 1, more than 0, then delta G is negative. This shows spontaneous and non-spontaneous questions. Non-spontaneous and spontaneous processes, sorry. Okay. Let's talk a little bit about kinetics of the reactions. Kinetics means the speed of the reactions, right? Kinetics what was important for us in the kinetics is the rate of reactions. And the rate of reactions, if you remember, depends on some factors like temperature, like the concentration. So basically, by increasing the temperature for endothermic reactions, temperature increasing, so the rate increases because endothermic reaction needs heat. If this is an exothermic reaction, then by increasing the temperature, the rate decreases, goes down. But in general, with increasing the concentration means the number of molecules are more, the number of collisions are more, then the reaction happens better. So the reaction rate goes up. What is important for us in kinetics is how to draw the energy diagram in both kinetics and thermodynamics. So if this is the energy, the y-axis shows the energy versus the reaction coordinate. Let's say we're talking about, it shows an exothermic reaction, right? Exothermic. Why? Because the energy level of products is lower than that of the reactants, means the reaction has released heat. So what we need to know is, first of all, this is transition state. The top of the peak is called transition state. And the difficulty of a reaction is this part, where reactants change to transition state. The distance between reactants and transition states is called activation energy. This is the amount of energy which is needed in a reaction to take the reactants, unlock the reactants, break the bonds for the reactants, to take them to transition state. So this is the difficulty, just like climbing a mountain or a hill. As soon as you get to the top of the hill, going down is easier, right? So the distance between reactant and transition state is called activation energy, and the distance between reactant and products is called delta H of reaction. Standard of the reaction. So this is what you need to know and what you need to be able to calculate based on the given data. So transition state has the highest energy. Activation energy is what needs to take the energy level of reactants to the transition state. Now on page 14, if you're supposed to combine thermodynamics with kinetics, let's see how we can draw these four energy diagrams. Fast exergonic reaction. So fast means low activation energy, right? The lower the activation energy, the lower the distance between reactant and transition state, so it's gonna happen faster. Exergonic, so this is kinetics. Exergonic means the products, energy of products is less than energy of reactants. It should happen spontaneously. So if you want to draw this energy diagram, first reactants, products, this is exergonic, and this delta E shouldn't be too, activation energy shouldn't be too high. If you want to compare it to slow exergonic reaction, then slow means high activation energy, and exergonic again means energy of products less than that of the reactants. So products is still less than that of the reactants, but this distance should be higher. So you show it like These are reactants, these are the products. Okay? So I'm sure now you can talk about fast endergonic and slow endergonic. Fast again means low activation energy. Endergonic means energy of reactants is higher than that of the products. So, sorry, the energy of products is going to be higher than that of the reactants, endergonic. So you will have reactants, products, and again, not a very high activation energy. But slow means high activation energy, and energy of products is less than that of the endergonic again. Sorry, I don't know why I keep saying that. Energy of products more. So the distance should go higher. And this is the meaning of slow endergonic reaction. So and this is a transition state, right? The transition state is normally shown as this. And you can have more than one transition state, like the diagram shown for you on page 15. It says energy. This is a reaction coordinate. So a reaction is given. What is the overall reaction? The distance between reactants A plus B, or I'm sorry, AB, the molecule AB, and then you will end up having molecule BC. BC is lower than that of AB, so it's an exergonic reaction. And so the first transition state, the bond between A and B partially breaks. So this is the first transition state. And the distance between the reactant and this transition state is activation energy for the first step, 1. We call it activation energy 1. Then we have here an intermediate, because atom C is going to be involved, because the bond is supposed to break between A and B and C stick together. So the second level between intermediate and the second intermediate is the second transition state is going to be activation energy 2. And then you see the new bond is forming between B and C. A is in the system, but because we don't need it, we don't focus on it. So the bonds partially break between A and B. C approaches to B, and then bonds partially form between B and C, the second activation energy, and then at the end BC is formed plus A and some other products if you have it in the system. So we have a delta H for consider the first half-weight product is delta H1, and between the product and here, this is going to be delta H2 because this is the reactant for the second level, the second step, and this is going to be the product, because delta H is always between reactant and product, reactant and product. So the difference between delta H1 and delta H2 here is going to be delta H of reaction. Okay? This is delta H2, this is delta H1. The difference is going to be delta H standard of reaction. This is what you are supposed to be able to calculate based on the data and the given diagrams. One more thing you need to know is the effect of catalyst on the activation energy. Again, if this is the energy and this is the reaction coordinate, if, for example, this is a random reaction, if this is the activation energy without a catalyst, when the activation energy is high and the reaction happens very slow or it's almost impossible to happen, then there is a catalyst added, which might be light or might be heat, or as you saw, lightning. So okay, so this is the second activation energy with the catalyst. I call it EAC with the catalyst. So we have those catalysts in our body, which are called enzymes, and so because some of our reactions inside our body happen very, very slow, that we need some catalysts for them to happen. And finally, let's talk about the rate, because in the next two chapters we will start talking about alkyl halides and two types of reactions in them that happen in two different mechanisms, two different ways, and you need to know how their reaction happen and what would be the mechanism. So AB, let's say we have AB, then we have the bond breaks over A plus B. This is what we had, its diagram previously. We just worked on it. And then B, C. So this is a step 1. This is a step 2. And you saw, I erased the diagram, but if you go back to the previous page, you saw the activation energy for the first step was much higher. So this is your slow step. We said the higher the activation energy, the slower the reaction, right? That's the slow step. The slow step from general chemistry 2 is called rate determining step. And makes sense, the slowest will determine the speed of the reaction, or we just call it RDS. So the rate of the equation, if again you remember, is written based on the slow step only. And in the slow step, in this particular reaction, you only see AB involved, right? So again, one more time, rate equation is written just for rate determining step, for the slow step, because that's the step that controls the overall speed of the reaction. So rate, if you remember, was written as K, rate constant, times the molar concentration of the molecule or molecules involved. Here you just have one molecule. And if you remember again, the overall order of the reaction is 1, first order. But if you have a reaction like this, C attacks B and they kick out B at the same time, everything happens at the same time, then you will see this is the only step, so it would be the rate determining step. And what you see in the rate determining step, both molecules A, B, and C. So rate is going to be written as K, AB times C. Okay? So it's a second order remember? 1 and 1. So the overall order was second order, and this one was only first order reaction. Again, if you forgot everything about this stuff, a general chemistry review is going to help. You're not going to stop on the previous concepts. No time. Okay, I do part A, you will do part B. What are we supposed to do? Write the rate equation for each reaction. What's happened here? Seems like OH has attacked Br. Is it? Let's not worry about the mechanism. I don't want to confuse you with the mechanism. That's all. Don't worry about it. You don't have to show layers at this point. You will have them next chapter. Plus H2O plus Br. Bromide. So what happened is just happened, the reaction happened in one step, and in this step both of these molecules are involved. I told you we will be working on alkyl halide, and this is called an alkyl halide. So rate equation is K times alkyl halide times OH is a second order reaction. Do it for B, which is first order reaction. And you can work on the practices given to you, the problems given to you at the end of this chapter, working on the energy diagrams. If you need any help, let me know. It's just labeling the diagrams the same way I showed you. And good luck with the studies.